In this work, we employ homology area as a path distance function for clustering large datasets of paths. Path clustering is a machine learning method to partition a set of paths into subsets of pairwise similar paths. Such methods have been shown to improve the performance of tracking and motion prediction. Since the set of all possible paths in the plane forms an infinite dimensional topological space, distance-based methods often have to be used in order to perform path clustering. In general, algorithms for pairwise distance calculations for paths are expensive to compute, making them hard to scale for large datasets. Furthermore, they don't take into account the topology of the space where the paths reside and are therefore oblivious to the effect of the obstacles in the environment. In our work, we focus on analyzing paths between designated goal regions. By collapsing these goal regions to a single point, we reduce the problem to that of analyzing only paths that share both an origin and a goal. Subsequently, since all pairs of paths now share both an origin and a goal, for each pair we can concatenate the first path with the reverse of the second path to form a loop. We then use this loop to define the distance between the paths by computing the region enclosed by it, and checking whether or not it contains an obstacle. If it does not contain an obstacle, then the area of this region is well defined and it provides a distance between the two paths. If it, however, does contain an obstacle, then the distance between the two paths is deemed to be infinite. To perform these calculations, we use homology since it allows us to detect holes in the space, which intuitively correspond to obstacles in the environment. It also has the advantage that it reduces the task of calculating a region of the space delimited by a closed loop to solving a system of linear equations. Using the linearity of homology, we were able to show that homology area satisfies the triangle inequality. Furthermore, we devised a method by which we can drastically reduce the amount of regions that is necessary to compute for a dataset of paths. This allowed us to observe a significant improvement in the time required to calculate a distance matrix over using an off-the-shelf method. If you would like to discuss the details of this work, please come by our poster.